So in this video I am going to show you one of the most important and critical aspect of time series data representation. So it is none other than monthly plots and annual plots for a large time series data. So in this video I will show you how you can deal with long-term large time series and use them to interpret more meaningful information. So for this video I am going to use a monthly mean temperature anomalies dataset which published by GISS Surface Temperature Project. So if you look at the dataset, it has data starting from 1880 January to all the way to 2016 December. So I am going to use a dataset which denotes the monthly mean temperature anomalies in Celsius degrees. So as usual I have set up my web directory and read the CSV file which is H2LA global temperature CSV, and then we'll see how the data is arranged. So as I mentioned before, it has data starting from 1882 all the way to 2016 December. So first of all we have to create a time series object. For that I am going to call the starting day, call this smove variable, because for the time being I am only considering about this GCAG column only, and then I am going to call this create a time series variable by calling this particular variable, and I define the starting date and dates, and here I am specifying the frequency as 12 because we know these are a monthly data set. So as I mentioned in previous lectures, frequency as 12. So we can plot this graph. So if you zoom in, you can actually see a slight increase of the temperatures over the course of a period. However, you can't actually get a smooth line because you are plotting the actual mean temperatures. So by calling this season plot function, you can plot the seasonal variation of this each course of the period individually for the each year, all the particular data set or the time series object, and then we can specify the year labels, and we can specify the year labels to the left corner, and we can give these default parameters and then give the main topic of the graph, and also we can use the axis label and y-axis label. So we'll run this. So we'll zoom in. So by looking at this, you can't actually get a clear idea how the data is arranged. The main reason is that we are considering data all the way from 1880 to 2016. So in order to visualize and interpret better, I will just reduce this period starting from 2000 to 2016. So now it is quite clear. So we can further reduce the number of years displaying here. So we'll just limit to around 5 line graphs. So we can change it to 2010 onwards. Now let's see. So this is much more comprehensible than the previous plots. So in here in January you can see for the considering period, the 2012 anomaly temperature is high when compared to other periods. So in 2015 there is a very low temperature anomaly mean value for the January. So you can use season plot function to annual graphs for the considering periods. So in addition to that, you can also have monthly plots also. So in here we can call this month plot function, and we can specify the data time series object, and likewise we can same variables that we used for the previous. So if you look at this, you can see how temperature has changed, or the anomaly mean has changed for the given years for each month of the year. So in here you can only see about few years, because we reduced the time series date range. So we can increase to the around 2000 year, and then run this again. So now you can see that it shows more variation in terms of mean values. Even though this gives some information, it is quite difficult to make decision making based on this data. Therefore I'll show this data. Therefore I'll show you the box plot, because it is much more comprehensible than the monthly variation plot. So if you zoom in, you can see the temperature usually increased in the month of May, and also based on this box plot, January is the lowest monthly temperature anomaly. Therefore, finally we can assume, or that interpret, the month of May is the highest temperature of the year. Also, to smoothen the seasonality over the years and remove other spikes, we can always use the monthly or the moving average for an entire season. So in the next part, I am going to show you how we can conduct monthly moving average or the yearly moving average for the data set. So first of all, I am going to show a 1 year moving average. So we know we have data for the monthly periods. So in here we are going to assign the order as 12, because for the 1 year moving average we are considering 12 months mean. So now let's see. So now you can see a very smooth graph removing spikes. So the main advantage of this is that we can get a sense of how temperature changed over a long period of time. So we can increase this order to 36. So in here 36 indicates a 3 year moving average. So let's plot this. So now you can see it has further smoothened. However, in this case I have only selected data from 2000 onward. But if we choose the data range from the starting of the clear sense of the trend, so we'll cause this. And then change the time series period. And let's run it again. So by looking at the 1 year moving average, you can clearly see the temperature has been increased over the course of the period. So now we'll compare it with the 3 year moving average. So it has further smoothened the graph, and likewise we can get a long-term idea of how the data is distributed and the trend of the temperature variation. So in here I have selected a very long-term moving average, which is 10 years, and let's run this. So the 10-year moving average further smoothen the graph. So likewise, if you want to get a long-term perspective, you can always use a 10-year moving average, or even higher if you have a very long data set. So likewise, if you have a dense time series like covering a long period like 2 or 3 decades, you can explore both seasonality across different months for every year, and also get an perspective by plotting the moving averages. So thank you very much for watching the video.